that, just speaking bluntly, pisses me off. You're not being professional. I don't give a shit. So what they do is they'll solve for dx, right? They'll solve for dx. So they'll multiply by 2, and they'll multiply by x to the 1/2. And it makes students think that everything is doable because I just replaced dx with this. But can I do that? Will that get me to where I need to be? You guys cool with that? Can I solve for dx? Multiply by 2, multiply by x to the 1/2, yes? So if I replace dx with this, why is that not good? What is my whole purpose with u sub? I want to take everything that has x and make it into something with only u's. If I put this in here, I got x still. Yes? Okay, so I just wanted to put this in case anybody has experienced that. That's bullshit. Sorry. I got to be a little more professional. That is an acceptable method, but it opens the doors to some major mistakes. Okay. So this obviously is not the right way to go. So here is another level of flexibility with u substitution. U is the square root of x. So I know this is going to be e to the u eventually. If u is the square root of x, what is x? U squared. I love it. Especially because I know from 0 to 1. Right? There's no weirdness with whatever. So then what's dx? 2u du. Yes? So this, we've seen an example like earlier. We did the u equals x plus 2, and then we subtracted 2, and we knew what x was. This is the first time that we write what u is, and then we solve for x, and then we take the derivative. But do you see how nice this is? Now, if I do this, I can just replace this directly with 2u, I'll put that out there, du. That's dx, yes? Did I replace all the x shit with u shit? Yes. And then what I have to be careful about with these? Yeah, when x is 0, u happens to also be 0. When x is 1, u happens to also be 1, right? But you got to be sure. Some of you guys are being very loose with your limits. Don't do that shit. I'm going to show you an example, I think. Yeah, why not? Of what I used to do as a student. That is acceptable. But I've come over time to appreciate not doing it. But I'll show you. So that's one. Now do the same thing with the other two that they gave you. On this one, you're going to have to remember your double angle formula for trig.
Oh, no.
Or you're going to have to look it up. Right?
Sadness.
Oh, man. I got to look something up. All right. Okay. If you're going to, remind me, who's going to Calc 2? Anybody still have that in their plans? All right, you're going to need to know your trig. Holy shit. Two of the first things you do is trig intensive. Yes? So if you don't know your identities, if you don't know the basic values, that's right. You got it. All right. All right, Jeff, I think you got the idea. Okay. All right. And the rest of you, you're still in this class. And I'm going to put some trigonometry on this next freaking thing. I tell you that. And on the final. Oh, yeah. So you got to know the identities that I kind of told you earlier that you're supposed to know. Yes? And I'm going to test to make sure you know. Okay. Anything else from homework before I show you something real quick? Okay. Okay, so real quick. If I had, I don't care, let's say this. Right, this one should be pretty simple, right? What would you let u equal? X squared, then du is 2x dx, so I need a 2x here, right? So now I've got the parts to create my du. And then this, of course, will be e to the u. Now, here's what I did as a student, because for some reason, I hated changing the limits of integration. I just didn't like it, even though it's pretty simple, to be honest. But I just want to give you an option, and you got to be careful because not all teachers are going to like this. And as I show you this, don't do this. I don't know. I'm just going to show it to you. Because it becomes really important later in mathematics about the limits, and you have to be very careful about the limits. And if you're a little loose now, you're not going to be that cognizant of how important it is to be careful with your limits. But let me just show you. Some of you guys sort of do this already. If I don't change these, what is wrong with me writing this? What am I saying is happening that isn't actually happening if I write this? No, I haven't done any integral. So I've rewritten the integral, but I have written the limits. And what are the limits supposed to relate to according to this integral? U. Is U going from 1 to 2? Hell no. What is U going from to? 1 to 4. So what I created myself as a student, and this is a part of making math your own, right? And then working with the teacher to say, I'm just going to do this. What I used to do this. I used to put little parentheses to remind me that that isn't what U's doing. Now, technically, that's wrong. So I kind of advocate against this. But I notice some of you guys are sort of being really loose, and you have to at least be aware that you can't write the same limits when you go to U. So how are we doing this then? What is the integral of e to the U? Incredibly enough, it's e to the U. Yeah. And then I'm going to bring my x back. Is that cool? So now I can put 1 and 2 in. Is everybody cool with that? It would be 1/2 e to the U, and U was x squared. So if you come back to x at the end, then you need to plug the original limits in, because that's what x is doing. But why not just make this 1 to 4? Where did I get 4 from? Yeah, because when x is 2, U is 4, and x is 1, U is 1. 1/2 e to the U, 1 to 4. Right? Not a big deal. In fact, it's slightly better to do it this way. Because like I said, later, it's going to be a lot harder to backtrack. You're going to have possibly multiple substitutions, and you really don't want to try to backtrack to the beginning. That's just a little insane. Okay. Maybe. Okay. So some of you guys know what I'm talking about. Some of you guys are a little loose with this, but when you change U, you've got to indicate these are wrong, either by changing them or doing something to tell yourself and me that you know that these are not right. Okay. Anything else before I get back into where we left off? Okay, so what I want to do, everybody has this here, this beautiful thing here, very festive. You need it? Okay. I'm very proud of this, to be honest. I can't remember how long ago it was I made this thing, but I remember as a student, I had a ton of trouble with this, just to be upfront with you. And it was mostly because the way my instructor presented it. I couldn't put things, I'm like, I have no idea why we're doing this. I couldn't put shit together. Of course, they had less animation resources available to them, but still, they could have explained things a little bit better. Hopefully I'm doing an okay job, even though this is weird as shit. We talked about discs and washers. Yes? Yeah. Anybody else need one? So what I want to do, before we do anything here, and the whole idea with discs, it's almost too nice to believe, but if I have a function, so here's my original function was this right here. And of course then we rotated it to create this kind of pedestal looking thing, yes? You guys, if I turn this way, it's a pedestal kind of thing, yes? Anytime I do a rotation, the cross sections will be circles, of course. Every point on this, if I rotate it, it's a circle. So it doesn't matter how freaky the function is, if I rotate it, cross sections are circles. Okay, maybe. So the disk method says, let me figure out, as I move along the x-axis, that's why it's dx here, as I move along the x-axis, let me find the volumes of these disks, which is the area of the circle times the width of the disk, which of course is dx. It's how much I'm stepping on the x-axis. Are you guys kind of with me? So we're sort of a quick review of what we've talked about already. And of course, if I add up, if I integrate this, I add up all these. The radius, of course, will be this distance here, which normally is the function, but it could, if the axis is offset, then it's going to be a little bit different. We did an example like that. Okay, but all it is kind of too nice to believe. The function is the radius. I want the area of the circle. Well, that's just pi times r squared, which in this case is pi times the function squared. And as I move, if my function gets bigger, my radius gets bigger, and that's a bigger circle, which completely makes sense. Okay, maybe. Maybe? Okay. So let's do this. Before we talk about this weird-ass thing, let's do some examples related to discs and washers and stuff. Can you guys very quickly just plot this here? What does y equals 0 mean? X-axis, kick-ass. So it's going to be bounded by the x-axis and those two functions or relations. Let's see, okay. All right. Is that cool? So it's bounded by the parabola, the line x equals 2, and the x-axis. So you get this funky little curvy triangle thing. That's going to be the first step in all this, basically, in most of these problems, is going to be just, can you graph the region they give you? Okay, I like it. And of course, if you do this in pencil, you can kind of graph the whole thing and then erase the parts once you find where they meet. Does that make sense? So that I didn't extend this because I didn't need to, because I just have to stop where it meets the next wall. Okay. Now I'm going to rotate about the x-axis. Or I could say around the x-axis. But I think the book says about the x-axis, which is nifty. So I don't need to do any 3D anything. I don't. I'm going to kind of set the problem up, and then I'm going to go back and do 3D if you want to. But so first question I have for you, if we want to use disks, what does the integral have to be? Integral d what? You guys remember? For disks, it'll be integral dx because it's always integral d. It's got to be if it's parallel to the x-axis, it's dx. If it's parallel to the y-axis, it's dy. This is the x-axis, so it's dx. And why does that make sense? Because once I rotate this, I'm going to locate my disks along the x-axis. So I need to move along the x-axis to find them. Okay, now, disks need basically this. So I just need to figure out what R is for any arbitrary disk. So what you can do is you just pick a spot, pick a location on your x-axis, and of course, depending on how much you understand this or not, you can be more or less detailed. What are you going to use, Jeff, here? Okay, what is this? Red. Okay. So let's just say I'm here. How do I figure out the radius? What would I draw in there that would represent the radius at that point once I rotate? What's the radius? The distance from... True, but now just tell me in general, what's the radius? The distance from the axis of rotation to the function. I like it. So when you do disks, you might have a hollow middle. You got to have an inner and outer radius and all that stuff, right? So it's the same idea, though. It's the distance from the axis you're rotating around to the function itself. So in this case, it does happen to be exactly the function, right? So my radius is x squared. I'll lock it. And I haven't drawn any 3D anything, but I can do the integral now. Yes? And you'll start to see why this is the most important step, is what the hell is d what? What makes sense? So what am I going to put in here? What's it going to go from to? 0 to 2, I like it. And again, we're looking along the x-axis, right? If this would have been dy, it would have been 0 to 4. 0 to 2. I can pretty much pull the pi out. Is that cool? And then r, of course, we've identified that as x squared. And now that's a pretty easy integral, right? So pi integral x to the 4th. So it'll be pi over 5 x to the 5th from 0 to 2. Is that cool? I'm sort of rotating my answer as I go. Spiral of an answer. Okay. And of course, is everybody cool with that? I mean, once you get the integral set up, you just attack it. It should be mostly pretty straightforward. Kind of like the way I said that. So now 2 to the 5th is 32. And 0 gives me nothing to worry about. So that's the answer right there. Now, let me come back and try to do some, what do you call it? 3D. Oh, this is always exciting. Okay, let me give myself a few places. Okay, so this would be like this. And basically it'll be like that. Okay, that's not bad for me. Although you can't really see it, but I will. All right, now, if this was a straight line, can somebody tell me what shape this would be? Cone. I love it. Does anyone remember the volume? So what I'm doing right now is extra shit. I'm doing extra shit right now. You never have to do this. I'm going to kind of see, does my answer make sense? So if I did make this a straight line, it's just a cone. I don't know if you guys remember the volume of a cone. Yeah, 1/3 pi r squared h. I'm with you. So it'll be 1/3 pi. The radius here is 4, right? 1/3 pi times 16, and the height would be 2. Is that cool? Whoa, shit, Jeff, show them what you're doing. 1/3 pi. The radius is 4. That's the radius across the top, of course. And the height would be 2. So this becomes, wait, Jeff, why do you put it? Oh, that's fine. I thought it was a square. So 32 pi over 3, which is bigger than this. And why is that expected? Why is it expected now I get a bigger answer? Because, yeah, if I make this a straight line, I'm adding this in, and it's rotating. All right. So at least I know I'm sort of in the right ballpark. The area I got is smaller than a slightly bigger cone would be. Okay, maybe you guys are with me. I don't know. All right. This one, notice it's the same region, right? It's the exact same region. We're just doing different stuff to it. So it'll still be there, 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 Same as before. Exact same starting region. Except now, what is my axis of rotation? Y equals -2. Where's that? What kind of line would that be? No. Horizontal. Right? Y has to stay the same, so it can't rise. So y equals -2. That's my axis of rotation. So when I rotate this now, what's the main difference going to be with the first one as an example? There's going to be a big old hole down the middle of it, right? Kind of funkadelic. So I'm going to have, what do I need to use then? I can't, can everybody see from this? There's an obvious inner radius and an obvious outer radius. Anytime your function, see if you guys like this. Anytime your function does not hug the axis of rotation, there's going to be an inner and an outer radius. There's going to be some gap, some hollow piece. You're going to have an inner part and an outer part, right? I lock it. Okay. Inner radius, can you guys see that? That's nice. What's the inner radius? Is that cool too? Yes? Because it's 2 away. And what's the outer radius going to be? So here's how you always do this. Are you ready? To figure out the radius, you take whatever is greater minus whatever is smaller. Does that make sense? How do I find the distance between this and this? I do this minus this. That's what distance is, yes? So what is x squared minus -2? Yeah, so you can see that's a freaking easy mistake to make, right? It should be more than x squared, because this was x squared, and aren't I further away now? So it should be bigger than x squared than it was in the last problem. Okay, I like it. Now how the shit do I set this up? Well, basically, the idea is still going to be pi, but now it's going to be r outer squared minus r inner squared. Because I'm going to do pi r outer squared, but what that would do is this would be filled in, and then I got to subtract this part when I rotate this. So it's really 2 disks, the outer disk, and then I subtract the volume of the inner disk. And I think of that as I'm drilling it out, right? Drill that middle part out. I also call it a cookie cutter problem, where you cut a cookie out. Yes?
Do you think of the distance as 2 plus the space?
Sure, yeah.
Okay.
Because that's 2 away from 0, so it'll be 2 plus whatever it would be normally. I love it. Okay. The thing is, you got to be a little careful, because, I can't remember if I do it on this one. Yeah, I sort of do one like that. The radius, I could have put the axis of revolution anywhere I wanted to, including like right here, for example. Right? If I would have put it here, then my radius would have been 4 minus x squared.
Yeah.
Okay. I like it. That would have been the inner radius. Yeah. Okay. So what does this thing look like? Hopefully, and I didn't make a big deal out of this, but why is this dx? Going across an axis that is parallel to the x-axis. I love it. So anytime it's parallel to the x-axis, dx for disks or in washers. Okay. And the same thing with y. Yes?
What if we're rotating it around the diagonal?
Ah, I love it. I was about to say that earlier. We totally could rotate around a diagonal line. That is a little bit beyond the scope of this course. But that's when things get really interesting. Can you imagine how that would be just a little bit or a lot more difficult if I wanted to rotate around like y equal x plus 2 or something? Yes? No? That would be pretty funky. So let's not do that yet. Okay. Maybe not at all. I can't remember now. I don't think it's in this. So help me out. This will be from what to what? 0 to 2. Good, because I'm still going, still the same region. And it got dx, so it cares about what x is doing. Our outer was x squared plus 2. Our inner was just 2. That kicks ass. And now that we got the integral set up, this should be the easy step. I almost don't want to do it, but this will be x to the 4th plus 4x squared plus 4 minus 4, right? That's kind of nice. Is that all right? Just FOIL out the x squared plus 2. And then the plus 4 and the minus 4 cancel. And then you just integrate. You get pi times 1/5 x to the 5th plus 4/3 x cubed. Evaluated from 0 to 2. And I'm bored with it. I almost don't care because now it's just plugging a calculator. Who gives a shit? Sorry, let me be careful. The answer is very important. I don't know. But I hope you guys understand what I'm saying. This is kind of boring. This is like throwing a calculator. I almost don't care what the number is. You just throw in the calculator, you get a number. Okay. Maybe. You guys with me? I mean, what would that be? 32 pi over 3 plus 32 pi over 3. Interesting. Is that right? Am I looking at that right? Yes, you are, Jeff. Good job, buddy. So it'll be 64 pi over 3. Neato. If I did that right.
No, it's over 5.
Is it 5?
The first one's over 5.
Oh, that's fine. I can't even read my own writing. All right. So then you have to get like who cares? Is that larger than this one? Obviously, right? Because this was 32 pi over 5, and this one's adding extra stuff. It's the same region, though, so why is this one so much bigger? This one's... Say again?
More to go around.
Yeah, it's taking this, and isn't it rotating it even farther over? So the whole thing is like wider, so this region goes longer through because it's further out. It's farther away from its axis of rotation. Okay. All right. Try this one here real quick. What's something you can do very first thing to make this easier so you can focus on exactly what you need to graph? What's the very first thing you can do? What's important? Why did I only graph this much when I did this? I mean, there's a lot more to these graphs. Why did I only graph this much? Because I can stop where they intersect. So the very first thing you should do here is figure out where they intersect. Because then you can focus your graph just on that region, right? Oh yeah, let's talk about that too. All right, so they meet at 0, x equals 0, and x equal 2. So this piece is the same from the first one, but then I've got this happening here, right? Crappity-doo-dah. Damn it. Jeff? Okay. My banana's got a stripe down the middle. I got a very, all right, that sounds weird. That's a smushed banana, basically. Yes? Okay, purple too. So it's really interesting banana. And I'm going around the y-axis. So if I want to use discs or washers or something, what would my integral have to look like here? dy. I like it. Which means all of the functions I put inside of it, of course, needs to be functions of y, 11. Okay, I like it. Okay. And well, let's see. Let's just keep going. Let me say this real quick. What if this would have been y equals x squared plus natural log of x minus e to the x cubed? Can you solve that for x? Almost doesn't matter what I said, but what do you think? Can you solve that for x? What if it would have been y equals sine of the natural log of x minus 7 tangent x? Can you solve that for x?
Yeah.
Do it.
I don't want to.
Okay. Do you want? All right, that might be a better question to ask. Even if you think it's possible, do you want to? No. Okay. I really want this to make sense. If I want to use discs in washers and I'm rotating around the y-axis, I must do integral dy. I have to. Yes? Period. End of story. And if my functions will either not easily get solved for x, or it's impossible to solve for x, I'm kind of screwed. Yes? If I can't, I can't go further. I'm screwed. That's where the next method comes in. It will always work when washers and discs don't, and sometimes they both work. Depends on how simple the functions are. But whenever washers and discs doesn't work, the other method will. Okay, that's just a little preview. That's why we're going to have a whole other method to learn. Yay! All right. And inside, of course, is going to be, let me just put pi outside. R naught squared. R outer squared minus R inner squared. I kind of gave away the next question, which would have been, do I use washers or discs? But if I rotate this around the y-axis, there's an obvious inner and outer radius. There's an obvious gap in the middle. So what's the inner radius going to be?
2x.
Yes. So the inner radius is 2x. And the outer radius, of course, x squared. I love it. Now, again, just to really get this through to you guys, I think you guys get this idea. I don't have to graph any 3D. I never graphed any 3D with this problem. I did it for this problem just because. Just in case you guys are worried as we got into this section, you're going to have to graph 3D to be able to do them. Yes?
Is it 0 to 4 because we're on y now?
I kick ass. I love it.
Okay.
Right? So now it's dy. This thing controls everything. dy, therefore the functions have to be functions of y, and the limits have to talk about what y is doing. I love it. What have I not done yet, though? If I start to write this, let's see. Pi, like you said, is going to go from 0 to 4, because that's what y is doing. What have I not done yet with these? I can't have them in terms of x, correct? I've got to solve for x. So my inner radius is currently y equals 2x. So of course, that becomes x equals y over 2. Is that cool? And my outer radius is currently y equals x squared. That becomes, and here's where I got to be a little careful, but see if you guys are cool with this. Solve that for x, what do I get? And why is it not negative square root of y? Right? Because officially, if I do this, I've got to do plus or minus. No. It could totally be negative square root of y. If I would have used this part
Oh.
of the parabola. But I've got this part. I've got the positive part. Everything's positive, correct? I'm in the first quadrant. I really want you to understand, if you have to solve for a different variable and you got to take a square root, it's a plus or minus. But you have to think for a second, do I have the positive part of the parabola or do I have the negative part of the parabola? Well, I get the positive part. Aren't the x's? So if I would have had this part of the parabola, right? Then my x's would have been negative. Aren't they negative over here? I would have had to take x equal negative shit. Yes? But I'm over here. X's are positive. Okay. I'm spend a little extra time on the parts that really confuse people. We're not used to having to worry about that too much. That's why I want to talk about it for a little bit. So what do I put in here now? I got my R naught. I'm sorry, I keep saying not. R outer is, let me make this official, square root of y, yes? R outer is the square root of y. Yeah, I like it. Minus R inner, y over 2. Become a square. Okay. And that's kind of beautiful, right? The worst part was going to be the radical, but it immediately dies. So you get pi 0 to 4, y minus y squared over 4. So you get pi 1/2 y squared minus y squared over y cubed. Become a 3 over 12. Is that cool? Right, because it'd be 1/4 y cubed 1/3, so it'd be 1/12 y cubed. And you can hear me slowly lose interest. Right? I got to be real careful because, again, obviously this is important. You got to get the answer, but this is just plugging shit in. You know, it's not compared to this other stuff. It's not quite as interesting. So you put this in. Let's see. You get pi 16 divided by 2 is 8. And 64 divided by 12 is something. I don't know. What is that? 16 over 3? Bless you. Yes? Okay, thank you. And then you get, is it 8 pi over 3? Okay. Woo! Hopefully you're getting something out of this, because the hardest part about these problems is what tells me what to do next, right? I mean, the next level we're going to have to talk about what the other method is, how it works, and how to tell when to use which method. That's going to be the next kind of level of stuff. See how far you can get with this one. Graph that thing. Let me leave this on there in case you're copying that down still. Funkadelic. do it on a fresh one. Let's see. Do I need to? I can't remember. We'll do it on a fresh one. So this thing is basically parabola fell over and it's opening in the negative direction, right? So it's going to be, and the very first thing I should do, so I know it's going to look like this, but I don't necessarily have to graph the entire parabola. Did anybody do the right first step, which is just figure out where these guys meet? So they meet at y equals 2, negative 1. What that's trying to do. Okay. So let's see. Where do they meet officially? They meet at, or can I do some more room here? Oh, it doesn't matter, Jeff. So they meet at something 2 and something negative 1. So remember, we've had this issue before. Now I know y's. When I plug it in, I get the x's. You got to put them in the right order. So when I put a 2 in, I get negative 4. When I put a negative 1 in, I get negative 1. Crazy. This is really nice because one of these things is just a line. So they meet at negative 4, negative 2, I'm sorry, negative 4, 2, and at negative 1, negative 1. So one of them is a parabola. It's going to look like this. Right? Pretend like that goes there. Okay. And the other one's just a straight line. So it's got to look like that. So we got somebody's nose. I don't know. Or this is a fat banana. I don't know. Something strange. So this is the region we're working with. I'm rotating it around x equals 2. Now what's one nice thing about that, considering we only know washers and discs? What's my integral going to be? Integral d what? No, come on. Whatever it's parallel to. There you go. Okay. Yeah. Whatever it's parallel to is what I do. So this is going to have to be dy, which is kind of nice because my functions are already functions of y. Although they're not really difficult to solve for the other one. Okay. This is our funkiest one yet. So I need to figure out what my inner radius is. Now to figure out the radii, you just always start at the axis and you draw until you reach something. Okay, that's the inner radius. Then you start at the axis, you cross through the first thing, and then you stop at that last wall. Okay, that's pretty straightforward, I hope, right? That's how you find them. Can somebody tell me what the inner radius is? All right, now watch. Okay, guys. Between these two, the inner radius goes from this to this, correct? Which one of those, this one or this one? Which one's bigger? Which one's bigger between this and this? Which one's bigger? X, this one is bigger, yes?
Yeah.
You guys with me? All right, so again, what did I say earlier? And this is why what I said earlier becomes really important when you start having the axis kind of going all over and your functions on the other side. Bigger minus smaller. Bigger minus smaller, right? The radius has to be positive. That's his job, is to be the distance, which is going to be positive. So this will be 2 minus negative y squared. Oops. So it'll be 2 plus y, 2 plus y squared. So for example, when y is 0, shouldn't the radius be 2 here, the inner radius be 2? Right, can you see it? So pick a y. When y is 0, why is this whole thing shaking? Is it that thing shaking? Is there a little earthquake? I don't know. There should be 2, and sure enough, when y is 0, it's 2. What about here? Shouldn't it be a little more than 2? If y is whatever the hell that is? Shouldn't it be a little more than 2? And it will be. Y is negative something, squared is positive something, plus 2 is a little more than 2. Okay. So you can always, whatever you pick for the radius, you can always just pick a couple places and make sure it makes sense. I hope you guys are with me. Okay? All right. So what's the outer radius going to be? Yeah, 2 minus negative y minus 2. So the outer radius is going to be y plus 4. I love it. So when y, for example, is 2, when y is 2, this says the radius is 6. And isn't that true? 1, 2, 3, 4, 5, 6. Yes, maybe. And again, I'm spending a little more time on this because the radii are normally the parts that really give people some trouble. They put it backwards. They don't have a minus where it's supposed to have a plus or whatever. But that is what you physically do to make sure, first, to pick it correctly, and second, to make sure you made the right pick. Right? Just take a few places and make sure it does what it's supposed to do. Now we can set up the integral. So this is integral. Let me see if I can pull out. Okay. Don't have to be that much. Okay. This will be integral. And it's going to be dy. So what's it going to go from to? Good? Yes? Yeah, negative 1 to 2. Yes, because I'm looking at what y is doing. And then it's going to be r outer squared minus r inner squared. So it's going to be, where'd it go? Y plus 4 squared minus 2 plus y squared dy. Oh, there's my dy. Too bad. Now, one thing about washers and discs that sucks is the fact that there's a square in it. Because whatever's in there, if it's gross, you have to square it, make it even, more gross. Are you with me? So the other method does not have any squares in it. That's kind of nice, right? Okay. So now it's just, and now it's the part that Jeff unfortunately said is boring, but it really is. And you're all like, all this is boring. Shut up. Minus, this will be 4. I'm going to change all the signs as I go. And this is just a big-ass polynomial. I'm not going to do it. I can't do it. But you would just integrate that. It's really easy. Polynomial, plug in the numbers. What to do? Okay, now. I want to give you guys a second. You guys all done? Write that down. I'm going to try to draw the next thing, and then I'm going to immediately show you a computer-generated thing, because I understand how poorly I draw. You don't have to comment. Now, so we have some motivation as to why we want a different method. In fact, let's do this. Let's make it more specific. Bum, bum, bum. I think they have an example I can do real quick. Sure. What if I had to do, let me just draw this real quick. 0 to 2. Yeah. And y equals 2x squared minus x cubed. And I'm going to rotate it. Where am I at? Rotating around the y-axis. think about this just for a second. If I want to use, so again, this is basically just an in-your-face example of what I was saying earlier. If I want to use discs or washers or whatever, this would have to be integral d what?
X. Y.
Yes, dy, right? Because discs and washers are nice. They're always, whatever I'm rotating around, it's the integral d that. Yes, or it's parallel to that. Okay. So here I'm rotating around the y-axis. It would have to be dy. Why is that not good for me? What would I have to do with this? Solve for x. And of course, it's not impossible. It isn't. It is. I'm not going to claim this one is impossible, but it is nowhere near anything I ever want to see. It's going to have multiple parts to it. It's going to be really gross. Okay. So, and I could put a function here that it would be actually impossible to solve for x by hand. Okay. Or I still want to say practically impossible. Okay. So I need a method that does the opposite of what discs and washers do. Meaning, I want a method that when I rotate around parallel to the y-axis, it's dx. And when I rotate around the x-axis, it's dy, because then that would handle the situations where I can't use washers. I mean, the main problem here is what I have to put here does not match with what I can put my function as. Okay, so here's the idea. I kind of like this region. Let me blow this up. You could just zoom. Be quiet, John. Wah! Okay. This is my lopsided ghost region. So if I'm going to rotate around the y-axis, here's what we can do. Let me see if they do this. No, they don't. Okay. What I can do is I can, how do I say this? Is this a good one to do this with? Yes, it should be. Gross. Okay. I can do this. Let me make a little. Okay. All right. And I could do that anywhere in here. And that sort of feels like Riemann sums again, right? In fact, behind everything we're doing is actually all the Riemann sum stuff, to be honest, because I could just do it again with volumes, but it'd be effectively the same thing. When I rotate this, let me see if I can get you guys on board. And of course, I didn't get myself enough room over here, but that's all right. This piece, if I rotate it, is it not going to look, all right, give me some license here. You know how horribly I draw, so you don't have to put this on your refrigerator, but that's really good for me. I don't know if you guys are cool with this. I only went halfway, correct? Of course, I only went halfway. I want to slice, but when I rotate this, that looks like a shell, like a cylinder that's got a big hole down the center. Yes? So that's why we call it a cylindrical shell. You guys with me? And I meant to bring in, I was going to actually bring in, I completely forgot about this. I was going to bring in a can of soup and do this, but have you guys ever, let me see. The volume of this thing is what I want to analyze next. So, the volume of this, can you imagine a soup can, since I didn't bring one in? Have you ever taken the label off a soup can for all those, send the labels in kind of thing? Or no? Can you imagine taking this label off? What shape is the label in before you tear it off? The label is cylindrical, right? With a hole in the... If you take it off and open it, what shape is it now? Rectangle. I love it. So the idea of the volume of this is going to be the surface area times the thickness. Because if I open that up, isn't it going to be like imagine if my label was thick. And then I take it off and it's a little like, I don't know, like a thick, not like a note card, but like a thick, what would that be? I have no idea. Are you guys kind of with me? It'll be a little rectangular thing that's got some thickness to it. The volume of that is going to be the area times the depth in that case, the thickness. Yes? You guys with me? A little bit? So if I take my soup can and I rip its label off and I open it up, first off, before I do that, what is the circumference in terms of radius? 2 pi r. And of course, we're going to say it's height. And then when I open it up, now, of course, it looks like this. What is this distance here? 2 pi r, of course, right? And this is still h. And let me make it a little 3D. Why not, Jeff? There. It's a little bit 3D. Sure. Oops. All right. So now this area is 2 pi rh times the thickness. And guess what we're going to call the thickness? The thickness is related to this. I'm sorry, go ahead.
Delta x.
Dx. In this case, this is drawn like delta x, but I'm going to let that go to infinitesimally skinny, right? Can we stop for a minute? So here's the idea. I am rotating around the y-axis, correct? How do I look? Where am I not going to just do this with all the? I'm just going to keep making rectangles. Yes, keep making rectangles. And as I do that, they're going to have their own little shells that they create. Their own little shells they create. Yes. And holy shit, this is falling apart. But that's too bad. And if I just add up all of those volumes, I end up getting the entire volume of this shape at the end. Maybe? No? Okay, maybe. I mean, there's some really nice pictures in the book. Let me see if they give you a decent little... Much better than I could ever... You've gone too far, Jeff. Here we go. Here we go. This is one that's kind of going the other way. Let me see if they give me one that's going the way I want it to. No. Dorks. All right, anyway. So this is one where they did a rectangle. Well, no, this is going the way I want it to. Okay. So there's my rectangle on the inside. And then I rotate, and then I pick another rectangle, rotate, pick another rectangle, rotate. And if I let them go to infinity, little rectangles that I rotate, then I end up with the actual shape after I spin it. So if I had this region, I spin it, I find all the shells, add them all up. It's going to be the total volume of the whole thing. Okay, so this would then be, what is the height of each of these shells going to be related to? Yeah, the function value. Of course, it also, well, we'll see. There might be, we'll get there. We'll get there. So the height in this case is the function value at each point. How do I locate the region that I'm going to make a shell out of? This is the key part. How do you find one of these rectangles? What axis do you go along until you find a certain rectangle? The x-axis, correct? I find a rectangle along the x-axis, even though I'm rotating around the y-axis. That's why this method lets it be integral dx. I'm going to scan along the axis perpendicular to the one I'm rotating around. And that's why I'm allowed to do integral d opposite of what we used to have to do with washers and discs. And that's why this method works anytime the disk method doesn't, and vice versa. And like I said, depending on how simple the function is, they both might work. Okay. So this is going to look like, and I'll add up. In this case, it's 0 to 2. Let's just make it a to b in general. Add up all of these volumes. So 2 pi r, let's just leave this all like this, h dx. Where this will be, normally it's going to be f of x. And this is interesting. In this case, if I go to this rectangle right here, what is the radius going to be? If I'm at this rectangle right there, what is the radius going to be? How do I find, yeah, sorry? X, yeah. How do I find this rectangle? I pick an x value. So what's the radius going to be? X. Now, of course, can I use Shell's method if I'm rotating around the x-axis? Yes. In which case there would be a y here for the same reasoning. Maybe. Okay. All right. Okay. So let's see. Maybe we can try a simple problem out real quick, and then we'll head out. Oh, let me do this. Let me show you a better representation of what I'm trying to say. I think my picture was not bad. It wasn't good either. Don't get me wrong. I don't think it was bad. So this is kind of nifty here. The one unfortunate thing about this is the thickness isn't really too apparent here. It's not very thick, but that's all right. Like the dx isn't very big. But here's the basic idea. As I open this up, as I rotate around, now what's nice about this is I can do this. If I remember which one of these. I can look from above. So you can see as I rotate around, I am creating that. So this one, Jeff? It's this one. That cylinder right there, this cylindrical shell here, right? Oops, I took a negative. There we go. So there's that shell in the middle. Comes 0 again. Okay. Did I want it to be 0? No. That's all right, Jeff. It's all right, Jeff. You'll be fine. All right. There. Okay. Okay. So this is a little bit better illustration, I think. So here's the original function they're working with. And then they rotate it around the y-axis. And there's my shell that I get. And again, how do I locate that shell? Well, I can change where it is. So I can go out further. And of course, I get a little squatter. And then I go up. And then I get taller. Okay. So I can scan it. I scan along the x-axis to find them. And that's why it's integral dx, even though I'm rotating around the y-axis. Okay. I think I've beaten that point into the earth. Let's see. Can I do a real quick problem? I can, because I'm the teacher. Nah. All right. Let me take like a really simple problem. Let's see. Bum, 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 bum. All right, let's try this. Yeah, so let's do y equals x cubed, y equals 0, x equals 1, x equals 2. Okay, so let's graph this region. We're rotating around the y-axis. Let's see, y equals 0 is the x-axis, x equals 1, 2, so at 1, x cubed is 1, oh crap, we're not going to make a beautiful scale here, doesn't matter, so it goes 1 to 8, and of course x cubed kind of does this thing here, roughly, well, that's really rough, it's okay, Jeff, it's okay, and then I've got my x equals 1 and my x equals 2, okay, so there's the region we're working with. So everything they tell me is a wall. There my region stops at. So some of these are going to be, they give us two functions. I'm going to find out where they intersect, and that's going to tell me where to start and stop. Or they're just going to directly tell me where to start and stop. I'm going around the y-axis. So for shells, that means I want to do integral dx. I like it. So if I wanted, I can draw in a representative rectangle. Where is that at? X. I love it. Kick ass. So I know, so I'm rotating around the y-axis. So what's the radius? The really nice thing is, well, shells has a lot going for it. I'm going to we'll do some examples. I want to see if you pick up on it. Yes?
Why is it dx if we're rotating about the y?
Again, two things. One of the main purposes shells exist is so that a problem I can't do with washers, and what makes it a problem I cannot do with discs and washers is if it forces me to do dx or dy, but I can't get the functions to match that. So I would hope another method we would create would allow me to do the opposite. If I need, so washers and discs would require dy.
Okay.
Shells then does dx. And again, and not just, I don't want you to remember that just because it's got to be the opposite so I have a way to do something. It really, really is, how do I locate the rectangle that I want, a representative rectangle? It's along the axis that is perpendicular to the one that I'm rotating around.
Okay.
So if I was rotating around the x-axis, my rectangles would actually be laying down. I would locate it along the y-axis. Okay, maybe. And again, we just got into this. It's going to take a little while to get used to it. And what parts do I need? Let me put down the general idea. Let me just put it down here. So a to b, 2 pi r h dx. So I need my r. What's my r going to be? We basically just identified it. X. When will your r not be x if you're rotating around the, well, I have to give it away if I keep going. If I was rotating it around x equals -1, then my radius would have been x plus 1. Same idea. Same way I find the radius for discs and washers. I just have to be careful about what the axis of rotation is. So I know r is x. What's h? Good, which is x cubed. All right, so now let's put this together. So I'm going to go from what to what? Good, dx. All I care about is x, 1 to 2. 2 pi r h times the thickness. And this is the reason I spent some time talking about the end integral. Is this three-dimensional? No. I've got inputs and outs. It's two-dimensional. So the end integral does not have to immediately relate to my object. It's an integral whose answer is equivalent to the volume of the object I have. So we've seen that happen before. We've done areas that had nothing to do with the original area. When I do a U-sub, it totally kind of re-puts it together. So we're used to that. Okay, maybe. When you get to Calc 3, if any of you are, you will do actual three-dimensional integrals. If you do. All right. And so now this is easy. This is boring. Sorry. Just going to be honest. Right? 2 pi over 5, x to the 5th from 1 to 2, and plug it in and get you. Okay. Okay, maybe. It got really hot in here, did it? Or is it just me? Okay. Makes sense. All right, that's enough, I think. I've put you through enough. Oh, whoa! Very important thing. Quiz. Do you want it
Monday.
Friday?
Monday.
And here's the trade-off. Here's the trade-off. If it's Friday, it's going to go up through. Finish your thought, Jeff. Yeah, it'll go up through 5.5, and if it's Monday, it'll include 6.1. Monday, okay.
Monday. Yes, please.
Not too bad.
Because that's one class. Like that we have one day.
Say again?
So will this be included on the quiz?
No, I just said it will go up through 6.1. This is 6.3.
So 5.4 to 6.1?
Yeah, the last 5.3 to 6.1, I believe.
5.3 to 6.1. Okay.
Monday.
Okay, yeah, because the other one was 4.8 to 5.
Let me help future Jeff out. Hey, future Jeff. We decided on Monday. All right.